There are a lot of different examples where these kind of situations can be used, and statistically you'll see a lot of those where we may draw marbles out of a bag. Um, we may draw cards from a deck of cards and those kind of things, and hopefully you've got enough familiarity with those where those type of examples will not be very problematical for you. I do want to go over something right quick right now at this point on drawing marbles from a bag with replacement and without replacement. So let's just say that we go through and we have in a bag we have 3 red, 2 blue, 4 green marbles, and so then just let's just throw in 1 yellow one. Okay, makes the calculations a little bit easier. That's a total of 10 marbles. So what is the probability of drawing this 1 yellow marble out of those? We're assuming that they're all the same size and that I can't tell colors with my fingers or anything like that. So if these 10 marbles are in a bag, this combination, I draw 1 out. What's the probability of drawing out the yellow one? Well, obviously that's going to be 1 out of 10, or it's going to be 10%. Now, if I go through and I put the marble back in, then that is going to be with replacement. Okay, so I put the marble back into the bag and I draw it again. Well, you can see that the probability of drawing another yellow marble is the yellow marble again is going to be 10%. But if I do not put the marble back in and I draw without replacement, the probability of drawing a second yellow marble is going to be 0. That is, after I've already drawn a marble out, the yellow marble out, the second marble is 0 because there aren't any marbles in there, or any yellow marbles in there. So with replacement, I would still have this same distribution. Without replacement, then if I drew out the yellow marble on the first one, then I would have 3 red, 2 blue, 4 green. I'd have 9 marbles in there, but no yellow marbles, so I couldn't draw it out. So let me give you some formulas for that, on how to predict it. And there are formulas associated with, and depending on whether it says with replacement or without replacement. Okay? Okay, so just I'm going to go through, and the probability of drawing, let's say, 2 blue marbles. Okay, so I go through and I draw 1 blue. The first chance with replacement, with putting it back in, is going to be 2 out of 10, and the second one is going to be 2 out of 10. So that's going to be about 4%, 4 over 100. 4% of the time, I can expect to draw 2 blue marbles. Okay? If I don't replace them, then the first marble, I have a 2 out of 10 chance of drawing the blue one on the first one, and since I did not put it back in, then I've got 3 red, 1 blue, 4 green, and 1 yellow. So I've only got 9 marbles in there. So I've got a 1 out of 9 chance. Okay, or a 2 out of 90 chance. Over here it was 4 out of 100. It's 2 out of 90. You can see that there's quite a bit of difference in that. This is going to be slightly greater than 2% compared to the 4% over here. So that is dealing with replacement and non-replacement. Another concept that I'd like to explain is the at least one. And sometimes you may go through and you may see where we ask a question and we say, what is the probability of drawing two or more marbles from or two or more red cards from a deck of cards or something like that. The at least one rule is going to be what we would call a complementary. Okay, so it turns out that the probability of drawing or getting at least one is equal to 1 minus the probability of nothing. Okay, of getting none. And it turns out that sometimes this can be very easy to calculate. For example, I go through and I say, what is the probability of getting at least one heads when I flip a coin 20 times? Probability of getting at least one heads when I flip a coin 20 times. Well, if you go through and try to calculate that out, then this is going to be a very difficult thing to do. But getting the probability of getting no heads, that's going to be 0.5 raised to the 20 times. So 1 minus 0.5 raised to the 20 times is going to give you the probability of getting at least one head. This is a lot easier to calculate. For example, if the sample space, if we had 3 coins, you could have heads, 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 tails, heads, tails, heads, tails, heads, 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 tails, 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 heads, tails, 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 heads, head, tails, tails, tails. Okay? 3 coins, 2 different ways that you can arrange those, and you have those 8 sample spaces there, those 8 possibilities. And you know that it should be 8 because that's 2 raised to the 3rd time. There's 2 ways to do it. 2 raised to the 3rd time is going to give me 8, so that helps a little bit. So probability of getting at least a heads every time is going to be 7 out of these 8. There's only one place here where I don't get a heads. Okay, so I could go through, do all this out, count them out, get 7 out of 8, or I could plug it into this formula, which is 1 minus 0.5 raised to the 3rd times, which is going to be, this is a half raised to the 3rd, so it's 1 minus 1/8 is 0.875. So you can see that doing the calculation that way is going to help you a little bit. Again, a lot of different information here, and we've got this set up so that we can go through and answer these questions if you have them and need something a little bit further, a little bit more of an explanation. I'm just trying to hit some of the things that in the past students seem to have had some difficulty with, and not intended to replace the material in the textbook, just trying to go through and to supplement it. So if you have any questions, then let me know, and we'll see what we can do about providing a better answer. Have a good day.